Good afternoon, everyone. Yes, today I'm going to be talking to you about lunar poles, something I've been studying since before it was trendy. Next slide, please. Okay, so today I'm going to cover why do we care, why the poles are important, talk about evidence for ice at the poles, and then talk about the lighting, both where is it dark and where is it light, present some of the new SMART-1 results, then talk about surface operations, what would it be like to operate at the poles, and also talk about future data, talk about some of the gaps we have in our knowledge and how we hope they'll be filled soon. Next one, please. Okay, so the poles are interesting for both operational and scientific reasons. The spin axis of the moon is it's almost perpendicular to the ecliptic plane, and this results in rather unusual illumination conditions at the poles. Essentially, if we were to stand at one of the poles, the sun would always be on the horizon, and every 29 days it would go once all the way around. If you could really hold your breath for a year, it would do this 12 times, and at midsummer, the centre of the sun would only be 1.5 degrees above the horizon, and at midwinter, it would only be 1.5 degrees below. Now, the sun itself has a solid angle of about 0.5 degree, and this means that, firstly, if you're in a topographic low, the floor of an impact crater, of which there are many, then you very likely never see the sun, so you're permanently shadowed. Conversely, if you're in a topographic high, if you're in a mountain close to the pole, you have the possibility to either see the sun all the time or nearly all the time. So permanently shadowed regions are interesting because they represent cold traps. It's been modelled that their temperatures are well under 100 Kelvin, and at those temperatures, any water molecules that enter don't have the thermal energy to escape. So over billions of years, water molecules that hey. My ventriloquist lessons are coming on great.
Now, you know this happened one time before when somebody from APL came.
We do special stuff there. So the permanently shadowed places are very cold, where ice can exist, and places which offer abundant solar light are interesting from an operational point of view for two reasons. The most obvious one is you've got abundant solar power. Actually, the most obvious one is it's light and you can work. Attached to that is you've got abundant solar power, and finally it's a relatively benign thermal environment. The temperature swing, if you're at the equator, is close to 250 Celsius between midday and midnight, whereas if you've got a constant grazing angle near the poles, you're a relatively mild 220 Kelvin without much variation. So that's much easier from an engineering point of view if you're designing hardware to operate for long periods of time. Next one, please. The South Pole is also interesting geologically from its location. It's inside something called the South Pole Aitken Basin, which is a 2,800 kilometre diameter impact basin, probably the largest impact structure that we know of in the solar system. When it was formed, it likely stripped the entire lunar crust that existed at the time. So you have the possibility for mantle deposits, or deposits from deep down in the moon, to either be on the surface or close to the surface. So if we have a lunar outpost near the South Pole, field expeditions might be able to find mantle deposits. It's a bit of a holy grail for geophysicists. And finally, obviously both poles are close to the far side, and the far side is unique in the solar system in that it's shielded from radio noise. The Earth is fairly noisy, and radio astronomers like the idea of using the far side of the moon because it's very, very quiet. Next slide, please. So search for ice. Ice is a major resource. Obviously you can break it down into oxygen for breathing. It's water itself, which is you need a lot of. And finally, oxygen and hydrogen is obviously what the shuttle uses. So you could actually have the potential to make your own rocket fuel on the moon. And that the long-term goal is to go to the moon in a permanent basis, and for it to be a site to then go and explore elsewhere in the solar system. And if you can make your own fueling station locally, it makes it, given where the moon is in Earth's gravity, in gravity well, it's much easier to go from the moon out into the solar system if you can use local resources. Particular example is that it's 2 orders of magnitude easier to extract hydrogen from ice than it is to crack it from normal dry regolith. So this lowers, if you can use local resources, you lower the cost and you learn to live off the land, which is part of what the vision is all about. Now, Clementine and Lunar Prospector both detected evidence for ice at the lunar poles, and I've got one slide on both of those now. And I've put at the bottom, the search continues, and at the end of my talk I'm going to talk about mini-RF, which is 2 radars going to the moon, which is my day job, that hopefully will answer this a bit more categorically. So to go to the next slide, Clementine was a joint NASA-DoD mission launched in '94 that orbited the moon for about 71 days. Did a number of useful things. Gave us our first good look at the poles with a digital camera, which I'll be showing lots of those images later. It wasn't designed to look for ice. Someone had the idea that you could take the communications equipment on Clementine, which essentially is like an S-band radar, and you could point it at the surface, and you could monitor that return on Earth. And the idea here is you broadcast right circular polarized signal. If that bounces off a normal dry regolith, you get a left circular polarized signal back. If you get volume scattering because you've got an ice regolith mix, then you get double bounce and you get the same polarization back. So you get an enhancement of the same sense. So one of the ways to look for ice is to look for something called the circular polarization ratio, which is same sense over opposite sense. And the other thing you try and do is you do this over the angle between the receiver, between the transmitter and the receiver. And the best analogy here is if you take a normal flashlight and you shine it at the wall, you get a little circle of light. And if you change that angle to the wall, you still just get a circle of light. If you have a bicycle reflector, however, as you start to point normal to the reflector, you get an enhancement, which is why you have a bicycle reflector. And it's the same principle here. You look for an enhancement at small beta angles, and that's another piece of evidence indicative that you have volume scattering because of ice. And this was done for 4 orbits, 2 at the South Pole and 2 at the North. The graph on the right here shows the circular polarization ratio for those 4 orbits. And you can see for one of them, the top line, orbit 234, you see an enhancement in the CPR around the beta equals 0 angle. And that corresponds to the ground track that did go right through the poles. Now, this isn't a conclusive piece of evidence. It's been, to pick my words carefully, it's been much discussed as contentious. Some people have claimed that you could get this from rocks or that the data wasn't analysed properly. But essentially, this is the first piece of evidence we ever got that water could exist near the South Pole region. The other piece of evidence, next slide please, comes from Lunar Prospector. Lunar Prospector was a Discovery class mission that went to the moon, and it carried an instrument specifically to try and address this problem. It carried a neutron spectrometer, and what the neutron spectrometer does, essentially it can measure hydrogen deposits, look for hydrogen deposits. And it did indeed find enhanced hydrogen at both poles. And this isn't a contentious issue. All the general scientific community accepts this as fact. And at the South Pole, the permanent shadow appears, the enhanced hydrogen appears to be correlated with the permanent shadow. But there are 2 main problems with the Lunar Prospector data. The first is spatial resolution. A neutron spectrometer is essentially it's a 4 pi instrument. It looks everywhere. So your spatial resolution ends up being roughly equivalent to your altitude. So the lowest Lunar Prospector went was about a 30-kilometer orbit towards the end of mission. So the best possible resolution they have for these hydrogen maps is 30 kilometers, which is a lot bigger than your typical permanently shadowed terrain. The other problem is it can't tell you what the chemical form is. It can only tell you that it's hydrogen. You can't use this to distinguish between solar wind hydrogen implanted on the surface or whether it's ice. But the fact that at the South Pole at least, the hydrogen does appear to be loosely correlated with the permanent shadow, again, it's supporting evidence that it could be ice. So neither of these 2 are conclusive, but together they do definitely point towards the possibility of ice. You're not going to get any more information from these data, which is one of the reasons for flying Lunar Reconnaissance Orbiter. This question is only going to be addressed, well, it can only really be addressed by going down on the surface and analysing it. But there's certainly room for a detailed orbital survey to identify the locations which look most promising for ice, and that's what's going to be achieved by mini-RF and other instruments. Next slide, please. Now, one question you often hear is, well, if there's no ice, that means we won't go to the poles. And that's not true. Whilst ice is a major resource, the poles haven't been chosen because of the ice for a human outpost. So ice is not a requirement going to the poles. And What isn't any doubt is that at the poles there definitely is enhanced hydrogen. So you definitely do have a resource, a useful resource there. It just might not be water ice. Basically, we're going to the poles because of the lighting conditions. We're going to the poles because you've got regions that receive a lot of illumination, and that benefits you greatly from an operational standpoint. So they put here, light is a resource too, which segues on to, next one. Okay. What you have here, this is a movie made up of strips, orbit strips from Clementine. This is the North Pole. It covers from about 80 degrees here. These orbit strips go from 80 degrees to the this is Peary crater here, North Pole's up here. And we did this analysis back in the late 90s. At that time, the estimate for the amount of permanent shadow that existed near both poles was fairly small. It was conservative, and it was based on the surface area of a few craters close to both poles. Now, what we noticed when we made this and looked at this is that ideally you'd have a camera that covered this whole region and took it every few hours, but we didn't have that. But we looked at craters quite a long way away from the pole, and even though now you can't see it, for the images when you could see it, it did appear that a fair portion of that crater might actually stay permanently shadowed. But because we didn't have the ideal lighting data to do this analysis, if you don't have good image data, because ideally what you'd like is a nice big image covering both poles every few hours over a whole year, so you can see, even though I talked about you don't get much seasonal variation, we don't actually know how much you get. Mathematically, you wouldn't assume it's much because of the 1.5 degrees, but there's nothing quite like an image to really, to know what you're going to see. But so due to the limited illumination coverage, we started to do work using simulations. If you've got perfect topography, you don't need images. You can put the sun in all possible locations. You can map out on the digital elevation model on your topography where it's lit and where it's dark. And we do have lunar topography. At the time we did this, there were two major data sets. There was a topography data done by Jean-Luc Margot, which was produced using Earth-based radar. And there was also a data set produced by Tony Cook, which used Clementine stereo. Neither were perfect, as I'll go on to. And also, we know from Apollo times what lunar craters are like. There's nothing magical about the poles. A 20-kilometer crater on the moon, typically all 20-kilometer craters to a first order have roughly the same shape. Therefore, a 20-kilometer crater at the equator will have the same shape as a 20-kilometer crater at the poles. And we have very, very good image data and topography data, particularly from the J missions, of topography of equatorial craters, so we can pick analogous craters and look for them at the poles. But next slide. So first thing we did is we took the topography data and we ran multiple simulations where we put the sun in the same orientation for which we had a Clementine image. And the reason for doing this is the only way you can really test your topography data is to do that. If your topography is right, your simulation should match the image. So for what you have here, the bottom left shows is the actual Clementine image. This is Shackleton crater here, so you've got a little arc, about a quarter of Shackleton rim is illuminated. The top left, you have the Clementine stereo-based topography with illuminated for the same conditions, and the main image is the radar topography simulated. A couple of key things to point out. First, if you look at what the radar simulates, it's pretty good. We were quite excited when we saw this. You can see it also predicts that just a portion of the Shackleton rim should be lit, and to a first order, this is the Galash crater. Again, it looks like it was predicting about the right amount. I should point out, that Earth is straight up. So in this image, the sun was coming from about 50 degrees west. Even though it looks not, the simulation using the stereo topography, it isn't as good. It's noisier, but to a first order, it also predicted what you see. But next slide, please. We then ran into problems, which is, obviously the Earth-based radar topography can only see the near side because it's taken from Earth. And what we found was, when you ran, here we have the same triplet of images. So here we have the Clementine image, and the sun is coming roughly from 180 degrees longitude. So the sun direction is directly from the far side. And we find that the Clementine stereo, again, predicts equally well, but fairly poorly, what the lighting is. Whereas the not unreasonably, the radar, the Earth-based radar topography totally fails to predict what is lit. So it predicts stuff will be shadowed when it isn't, and stuff won't be shadowed when it is. So and the reason I show this is, next slide please, is that the only way to test it, I'm going to mention this again, you've now got the Goldstone data, and that's come out, and it's really nice looking data. It really needs to be tested before. I mean, people took the radar DEM and they published illumination maps for the whole year, but they didn't bother to go back and test it against an image. All data sets have limitations, and it's easy to get excited and run with them too far. So even though the Goldstone data, it's clearly higher spatial resolution, and I imagine it's higher vertical resolution than the Arecibo-based one, the Margot one. But it's going to be important that it's tested using as many available image data sets as we can before people run with it and try and use it to calculate illumination profiles that you engineers are then going to say, okay, we only have to worry about a 40-hour eclipse here ever. That might not be true. Okay, next slide. So because we realized that the topography data didn't have a high enough fidelity for us to do the maps that we wanted, we do what all people do in that case. We use fake data. So we ran what's called simulated simulations. So as I mentioned, this is a radius profile of depth for a 20-kilometer crater based on the Pike work, where he looked at lots and lots of craters. And what we did, next slide, please. So what we did is, again, we tested it. So we looked at currently we looked at simple craters. So this is craters smaller than about 20 kilometers, which essentially are all bowl-shaped. Larger ones have a flat floor, but you're not looking at larger craters where you start to get features such as central peaks and terracing. So far we've just looked at simple craters, and we studied craters in 2.5 kilometer size increments. So we made these realistic fake crater shapes, and we placed them at all latitudes between 70 and 90 degrees, and we ran a series of runs to work out, for all those sizes and all those locations, how much permanent shadow does a simple crater have. And we came up with this easy to remember equation where you can feed in the diameter and latitude, and you come out with the percentage of permanent shadow, and then you can come out with an area. And what we have here we have a crater called Mouchet J, which is about a 17.5 kilometer crater. This was our simulated 17.5 kilometer crater with the same lighting conditions, and we were encouraged that, to a first order, the amount of the sun matches the amount of light on the inner rim matches what we saw in the image. So in this single simulation, the black in the middle is the instantaneous shadow, and what's shown here in the white circle is what we calculated to be the permanent shadow inside such a crater at that latitude. Next slide. So this image here that looks like one of those color blindness tests where some of you can see a number. What we then did is we mapped out all simple craters that didn't look too degraded within 12 degrees of the pole, and they're shown here in yellow, and we found that in fact there are a few key results. The first is you get permanent shadow a long distance from the pole. You're not forced into just a few craters close to the pole. So even 12 degrees away from the pole, these craters have a small portion of permanent shadow, which theoretically could be cold enough to, for ice deposits. And the other key fact is the amount. We're talking thousands of square kilometers of permanent shadow. So there are lots of locations for which ice could exist.
Can I interrupt with a question?
Yes. Yes, but as you go further away, it's that very reason that your temperature gets warmer. There's been modelling done. I have worked now to do modelling of that to work out exactly how warm it's done. There has been some modelling done by a guy called Vasavada who did consider that, but back then his work is very good. He had limited, back in '99 computers weren't what they were today, so all his craters are 32 by 32 grids. That limits how geologically realistic you can make particularly larger features. What we're doing now is we've produced a model using a Linux cluster so we can have much higher resolution grids. And one of our goals is even when you get permanent shadow inside a crater that can see the rim, you can get sub-craters. The moon has craters at all dimensions. And one of the possibilities that you might have is if you have a crater within that permanently shadowed region, that sub-crater will be shielded from the rim of the primary crater and could be exceptionally cold. So we've actually got a model, we're doing some modeling right now to try and see how cold that would be. A block of ice will not survive that. It gets too warm. Now, people are doing work to see exactly if when water ice gets introduced to a lunar regolith, what exactly does it do at the grain level? You know, how exactly does it absorb itself onto the, and does that need, in fact, a higher energy to then extract it? I mean, you can't get it sitting on the surface, but that doesn't mean, equally, if it gets buried fairly quickly, it potentially you could survive brief periods. But I think it's, from the point of view of planning, where might there be a useful ice deposit, it's very unlikely it's going to be somewhere that even sees the sun for a little while. Next slide, please. So now I'm going to talk about the lighting map. So we've covered where it's dark, and I want to talk about where we know about where it's lit. The majority of our knowledge still comes from the Clementine mission. And Clementine was in a 5-hour period orbit, and it imaged each pole every other orbit. So we have a snapshot of the illumination conditions every 10 hours. It's important to notice that the data were collected. Clementine arrived right after midsummer for the northern hemisphere and midwinter for the southern. And that's why these are mosaics I made that cover within 10 degrees of the pole. And one of the things that people often notice is, oh look, there's a lot more shadow, permanent shadow at the south than the dark. Not necessarily true. There's two factors. One is you've got more instantaneous shadow because it's winter. The other is some of these key areas here, which is where we now know from the radar, you've got craters like Shoemaker and Faustini. There's no data. Clementine only had 2 opportunities to see those craters. For whatever reason, for communication problems, it didn't get any images of those craters. So they show up, data gaps show up here as black. So that adds to sort of the, oh look, there's lots of shadow. Not true, and I'll be showing some SMART-1 images where we do see that reason for the first time. The data in what probably in current terms is medium to low resolution. Clementine was in an elliptical orbit where it changed perilume between north and southern hemispheres. So in month 1, it got 250 meters per pixel at the south, 500 at the north, and vice versa for the second month. It also collected some high resolution data at roughly anywhere from 15 to 40 meters per pixel, but I'll show some of that. Next one, please. Okay, movie number 2, Keep Them Awake. What this movie shows, this is a single Clementine frame covering the South Pole. This is Shackleton over here. It's been put onto a radar image just for context, because as you see, the actual frame contains a lot of shadow, which makes it fun when you're trying to pick match points between. So this movie was made using the first month of data, and it covers a whole lunar day. So we can look at a few regions close to the pole for a whole lunar day. Next slide, please. Now, our key findings was that because this is winter data, had we found regions that saw the sun for the whole day, you could make the argument that they would always see the sun. And we did not find that. We found 3 regions that received the most illumination. The data at the time said about 70%, but the data has limitations. We had to make quite a few assumptions. There were gaps in longitude coverage, and you had, at the very best, you had 10-hour gaps in between. So I often see this number quoted as gospel. I know how fallible I am. I would argue that we have identified where the most illumination is in the area. That the exact number we're not going to get until we get future data, but I doubt it's not going to be more. But it will be roughly that amount, but it shouldn't be quoted like to 4 decimal places. So we have 3 regions that receive the most, and what was interesting is we did a detailed illumination profile for these 3 locations, where if you stood there for the day and the sun goes once around the horizon, we plotted for what longitudes you would and wouldn't see the sun. That's shown in the next slide, please. So the outer ring here of the squares, for those of you sitting close enough, that's point A, which is right on the rim of Shackleton. The middle ring, point B, lies on a ridge about 15 kilometers away from point A, and point C was the 3rd point, which was actually on the rim of Dergelash crater. So you can see so for each given image, we have a data point marked yellow if that particular region was lit, or blue if it was dark, plotted as a function of subsolar longitude. And the key thing to point out is, for point A, the largest, these are 10 hours apart, so the largest eclipse we measured was of the order of 60, 70 hours. So that, and also when A was dark, B, which isn't that far away, was lit, with the exception of one point when the sun was roughly at 30 degrees east. So collectively, these appear to be lit 98% of the time, which again, even if that number isn't exact, it does raise the possibility that maybe with 2 sites you can get almost constant solar power, and once you go to 3 sites, if they're chosen wisely, then you've got a good possibility of constant solar energy. And A and B only being 15 kilometers apart, that's not that far. From an engineering point, he says, talking to the engineers, I would like to think that that is a sort of distance where once you started to have infrastructure on the surface, you could even run a cable, use a rover, run a cable. It's not like you're having to go hundreds of kilometers. You can tell me afterwards why I'm wrong. Next slide, please. So what we have here on the left, I made a mosaic which to using the high resolution data, which is about, and the reason for showing this is twofold. So this is Shackleton, this is de Glache. You can see there's an awful lot of gaps. This is all the data that we had from Clementine. So we have fairly limited surface coverage at this high resolution. But it still told us something interesting. We co-registered this with the illumination map. And it's important to remember that there's about a order of magnitude difference in spatial resolution between these 2 data sets. And what we found when we looked in detail is point A, B and C correspond to simple local topographic highs. The best example is probably point C here on de Glache, which is when we managed to co-register them, it's just a little hill. It's just a hill that happens to be superposed on the rim of de Glache. And so what this shows us is the places that will receive the most illumination. It's going to be serendipity. It's going to be it just so happens that it's locally high with a low horizon. Next slide. I've shown this again for a couple of reasons. This is a blow up of the portion of the rim of Shackleton and with the illumination map on. And I'm going to show this in a little while with the SMART-1 data because it shows it at high resolution. This is point A here on the rim, and this is point B here on the ridge. And this is shown here as this very large, several football field size area on the rim of Shackleton that receives the most illumination. And the trouble is, you've got an order of magnitude difference between the resolution between the surface image underneath. The fact is, this is an artifact of the fact it was fairly poor resolution data. We know from looking at the better data that this is likely split into 2 smaller regions, but when you look at it at low resolution, they merge to form 1. So from a planning point of view, I get nervous when I see lunar bases laid out on this oval and this is how it's going to be. We don't have the data yet for you to really know the exact real estate that you have to play with. What we do know is that such places exist and they're rough, the rough scale and location. Next. Yes. This is an image showing the much forgotten North Pole. So this image shows we did the same work with the North Pole data, where we took a day's worth of images, we co-registered them, hopefully good to a pixel, and the spatial extent of this map is a pixel had to be seen in all the images in order to be part of the map. And again, we used the same. We have a scale here, and we found the places in white received constant illumination for a day in summer, and we essentially found 3 regions. This is the underneath here is actually a Clementine high resolution mosaic made by Mark Robinson of ASU, about 40 meters per pixel. This is Peary crater here. It's about a 78 kilometer crater. The pole is about here, not where the cursor is. Don't worry. Yeah. So we're excited to find places that receive illumination for the entire day in summer, but we were careful in what you can only use these data so far. You can't say that those regions are permanently illuminated because this is a summer day. You can say that were you to work and play here in the summer, you're going to have places where you see the sun all the time. So that if you're going here for a month, 6 months, once we get more data, there is a chance that the North Pole ends up having better illumination than the South. The North Pole, everyone's concentrated on Shackleton, and particularly the press seem to say NASA's going to Shackleton. It's my understanding from talking to folks that you're using Shackleton because it's a good example. It could actually be the place. It might well be. I think it will be the place. But if you plan for Shackleton and then the future data tells you actually the North Pole is better, your engineering is just as valid up there. Next slide. So conclusions for this work was that there were no permanently illuminated places at the South Pole, possibly at the North. Extensive permanently shadowed regions exist at both poles that could harbour ice deposits. The highly illuminated areas are reasonably small and distributed. They're not all right next to the pole. And there is the potential for constant solar power by using more than one array of panels. Next one, please. So now I'm going to show you some more recent data taken by the AMI instrument on ESA's SMART-1 mission. Here we have a picture of Shackleton crater, so you can immediately see it's nice data. I will explain why you have a quarter of the image so bright. The AMI instrument used a 1024 by 1024 CCD, whereas Clementine was 384 by 288. So it has the advantage. Bigger images are much easier to play with from the point of picking match points between them, and also you get much better aerial coverage. You can see in some of the Clementine frames, because you're looking at a fairly small area, you end up with images which have almost entire shadow, which makes it hard to put stuff into a context. Normally when you do multispectral images, when you plan an instrument to take multispectral images, you have a camera and you have a filter wheel, and you take an image, rotate the filter wheel to different positions, and you end up with a bunch of images that are almost, co-aligned. They didn't have that on SMART-1. It's a very lightweight instrument. So they used a different approach. Next slide, please. Which is they stuck the filters directly on top of the CCD, which not a bad idea. So they used three main filters for multispectral: 750, 915, and 960, and these were done in this L shape so that they could take, as long as the spacecraft was able to fly orthogonal to the CCD shape, they could take three images in quick succession and get a small postage stamp and multispectral. Unfortunately, what happened is, for the majority of the mission, for thermal reasons, the spacecraft had to orient itself, so this sensor was actually more like a diamond. And because of that, they didn't take that as much multispectra as they hoped. Two other things. This 847 little 1/16 square down here was from a laser experiment where they beamed a laser from Mount Tidy in the Canary Isles. And finally, this big square up here, they left a quarter of the sensor with no filter. The idea being that you would use that for, particularly at the poles, where you want more signal to noise. The problem with doing that rather than using a neutral density filter or something is that for a given exposure time, you're also exposing all the pixels at the same rate. This one receives a lot more photons than these because it hasn't got a filter to block them, which means that's why you always end up with a quarter of the image looking. Basically, it actually swamps everything else. The images that I'm showing you, I've taken that quarter, taken it out, restretched the 3/4 L, and then posted the other one back in so you can actually see everything. It's not a great, it caused quite a few problems with analysis. Next one. So the AMI has improved our spatial and temporal coverage. First of all, it was in orbit for over a year, so we have the possibility of doing full seasonal variations. The SMART-1 was in elliptical orbit with South Pole roughly 300 by 3000. So Periloon over the South Pole and Apolloon well up over the North. This results in 50 meters per pixel over the south, which is roughly equivalent to the Clementine high-res camera, but I mentioned it's a bigger sensor to cover the wider area. And at the North Pole, about 500 meters per pixel, so roughly similar to those Clementine, the main Clementine image data sets I've been showing you. Next slide. So a few key images to show you. The first is, here we have part of Shackleton crater, Dergelash. Our illumination map's there, bottom right, so for context. AMI did see at this nice 50 meter per resolution large areas around the South Pole. And specifically, I'll show you, this region up here heading towards Shoemaker crater is where we had the data gap in Clementine and had no good surface coverage. So we've seen that for the first time. And I've got this box here is the ridge that contains point A and B from our illumination study. And everything I'm going to show you from now on, we're going to concentrate on this region, because this is the region of interest. Next slide, please. Okay, movie number 3. So this is a movie. This is a single SMART-1 AMI frame, and what I would like you to look at is this ridge. So you can see how difficult it makes it to follow when it suddenly appears in that quarter. But I want you to look at this ridge here. We'll let that go through one cycle. Great. Go back to the PowerPoint. I'm watching the clock. Thank you. So there's a few things to show you. The first is surface coverage. This is the high-resolution mosaic I showed from Clementine, showing the full extent of good, at that time, the best high-resolution data we have. This is just a few images of AMI, and already we've vastly increased. First of all, we can see all of the outside of Shackleton. We can see all the way to Shoemaker Crater. It's very good from surface coverage. Next slide. Now I've got 4 different images here, 4 different pairs of images. One of them is going to be the Clementine image, and then you've got a SMART-1 image at about an order of magnitude higher resolution. And the main thing I want you to do is I want you to, these were taken with the same sun longitude angle, but the AMI data were collected in summer, and the Clementine was, as I mentioned, was taken in winter. So there's actually a lot of information, if you take your time, you can get from these. You can start to do seasonal variations. But what I want you to look at is this ridge down here.
The ridge is at 8 o'clock outside
the
crater.
Yeah, sorry. The ridge is at 8 o'clock outside the crater. If you look at the rim of Shackleton, you'll see where there are 3 small impact craters superposed on the rim, and that represents where that ridge hits. So here we have an image where the sun is coming roughly from 90 degrees east. Next slide. And here we have one coming from almost the far side. And again, this is the ridge here. Next slide. Here we have it coming from roughly 90 degrees west. And you can see that part of the ridge disappears, but we still see this region here, which corresponds to point B in our illumination map. And next one. And finally, here we have where the sun is coming roughly directly from the near side, 0 degrees longitude. And again, we can see the ridge quite well. And the other thing actually that Paul discovered looking at these is when you look at the amount of inner rim that is illuminated, you see a lot more of the rim when the sun's coming from the east than the west. And this shows us that, in fact, Shackleton has a regional tilt. And this relates to the fact that it lies on the rim of the South Pole Aitken Basin. So Shackleton isn't just flat on a sphere. There's a regional tilt here, which affects when you do your lighting studies. Next slide. So this is just to show that this ridge is lit. If you were to stand on this ridge, you would see the sun basically whatever direction it comes from. You know, when the sun is from this direction, you see all this side of the ridge, including the top of the ridge, and the same when the sun's coming from the exact opposite direction. Next slide. So the conclusion is that the AMI images do complement the existing Clementine polar coverage and have enhanced our knowledge. The initial results do support earlier findings that zones of extended illumination exist near the South Pole. We found an area near the South Pole that appears to be lit for an entire day in summer. That point B, that sort of hill that's again superposed on the ridge that extends from about the 8 o'clock position, the top of that hill appears to always see the sun for the whole day in summer. And our future work will produce refined quantitative illumination maps using these data when I've been lucky enough to work in these by collaborating with the PI. The whole data set is due to go into the ESA Planetary Archive later this summer, whereupon there'll be more data available and everyone will be able to analyze it. Next one. Now, this is an image taken by the Japanese Kaguya lunar, which is currently in lunar orbit as we speak. And they had the excellent idea, which was to take a high-definition movie camera and essentially mount it on the spacecraft at about a 45-degree forward-looking angle. I don't know if any of you have seen any of these high-definition movies. They really are very stunning. And the camera was put on for EPO, for educational public outreach reasons, but there's actually quite a lot of science that you can get because you can actually see, at least qualitatively, topography because you've got this perspective view. And we have a snapshot here of the South Polar region taken from Kaguya. This is when Kaguya is coming over from the far side, heading towards the near side. So you have Shackleton Crater, here we have Dergelash, and you see Malapert Peak, which is about 86 degrees over, on the horizon. And when Paul looked at this, he noticed immediately that we can see our points A and B, and we can see the fact that particularly point B does correspond to a hill, topographic hill on this ridge. Now, Kaguya has a laser instrument, and they will hopefully all their data will be made available, and we should be able to get the first detailed topographic analysis of this region and do very detailed illumination studies. Next slide, please. So, surface operations. If you're going to work at the poles, you will get it is the best place to go from a light. You will be lit a lot more than you would at the equator, and that permits you to work for a lot more of the time. Certainly compared to the equator, where you'd get 14 days light and 14 days night, you've got much shorter eclipse durations to deal with, where you're just going to be sitting in there and surviving. However, nothing's perfect. Imagine that. The best locations are very localized. We already know that. The places that receive the most illumination are dotted around, which means that if you're conducting surface operations, you're going to have to be careful that you don't get caught out in the dark. You're going to have to do really detailed illumination profiles of your whole region that you're going to work in, because you're only going to have a few localized best places to go to shore up. A lot of time, a lot of places are still dark. And you still get eclipse periods into the tens of hours. We'll know the exact numbers once we get either very better illumination data from LRO, or get a good laser topography data that we can then test against images. Even though if you model what a spherical, everyone likes a spherical moon. If you model a spherical moon, if you're at the poles, the surface temperature is about 220 Kelvin. It doesn't vary much. However, unless you get astronauts just lie down all the time, that isn't how it's going to be. You're going to have people standing up, you're going to have structures. A vertical structure at the pole receives the same input from the sun as a flat surface at the equator. So you're still going to get temperatures in the 400 Kelvin region that you're going to have to be able to deal with. Nothing is that benign. Also, from an operation point of view, the sun is always on the horizon. So you're always going to have long shadows to deal with, which can be awkward from a navigation traversing point of view. So you might even need arc lights, or something. You might have to illuminate large portions of where you work, even though you're seeing the sun all the time. And finally, you've got issues with direct Earth communications. Normally, you see the sun for 14 days, and then you're in radio silence for 14 days. So unless you've got a comm asset in place that you can talk to Earth all the time, you're going to have an awful lot of autonomy. Next slide, please. So now I'm going to finish my talk briefly touching upon what data we would expect to have in hand within the next year or so. The Indian Space Research Organization is flying their first lunar mission called Chandrayaan-1, which is scheduled to launch in the fall of this year. It's a 2-year duration mission in a 100-kilometer circular polar orbit. It has 11 instruments on board. 5 of them are Indian or indigenous, and 6 of them are international contributions, including so that the mission as a whole will do high-resolution remote sensing, both in visible, near-infrared and X-ray. It also has a laser instrument, so it will get global topography. It will also get global low-resolution mapping of key elements. And it's flying MINISAR, which is a radar that Paul and I are involved in, which is specifically designed to look for ice deposits near the pole. I've got a few slides on that right at the end. Next slide. Often when I talk about Chandrayaan-1, people seem surprised that, that India has this capability. They really shouldn't be. India has a huge indigenous space capability. It has its own telecommunications and remote sensing satellites, has its own launch vehicles. We're launching on a PSLV, sort of a Delta II class launch vehicle. And they're very good engineers, and they've managed to take a fairly small spacecraft and put on 11 instruments. They even managed to cope with the fact that the President of India is a scientist, which is good at one level, because it's a huge amount of political support. They have They get a very good high top cover. The trouble is, he's interested. We were at one of the science meetings fairly early on, and I think it must be PDR, so preliminary design review. They basically thought they had their spacecraft done, they had their instruments done, and the president's there and he's giving the talk, and he goes, what you guys need to do is add an impactor. You see all the engineers sitting in the corner going, no. So, but they did. They came up with something called MIP, Moon Impact Probe, and it's going to fly, and it's going to test technologies to help them with future landed missions. So they were able, even a long way into the design process, to take that curveball thrown at them about, just add an impactor. And the reason it's called Chandrayaan-1 is because there will be a Chandrayaan-2. This is a serious program. They will do a series of missions. No one should doubt that. Next, please. Launching next year is NASA's Lunar Reconnaissance Orbiter, whose primary goal is to collect data to help with putting humans on the surface in the next decade. It'll be normally a one-year mission in a 50-kilometer orbit. After that, depending on the amount of fuel that's left, it will stay in a 50-kilometer orbit until the fuel gets down to the point where they have enough to go into a 30 by 216 elliptical orbit, which is very efficient. It doesn't take much fuel to maintain, so we'll then end up in a 30 by 216 for a much longer period of time. So it has 6 instruments and a technology demo, which is the second part of our mini-RF, second radar instrument. So the LRO camera will acquire global 100-meter spatial resolution multispectral data, and it'll produce an illumination map at the 100-meter scale by imaging both poles every orbit. LROC also has what's called the NAC, a narrow angle camera. It's actually 2 cameras side by side, and this will collect data of 10 kilometer by 10 kilometer regions at 50 centimeters per pixel. So you're almost getting to the mapping out boulders to avoid type level. LOLA is a laser instrument which actually consists of 5 laser spots, and this will produce a digital elevation model at both poles of better than 50 meters per pixel. LEND is a neutron instrument that will make more, hopefully better maps of the hydrogen concentrations near both poles. LAMP is Lyman Alpha instrument, which essentially uses starlight to look inside the permanently shadowed regions. If there is a surface frost, which is an argument we're not going to go into, then it would see it. And the last 2, Diviner will measure the temperature, and the temperature is another key parameter. Surface temperatures inside permanently shadowed regions are done by modelers, and I'm a modeler, so I know how bad that can be. So what Diviner will do, this will actually collect real data, and that will be useful to modelers because we can predict. The physics isn't that hard, but you have to make certain assumptions on surface structure and composition to predict a temperature. If we start to see temperatures that are very different to what we predict, we can invert that and use that to actually learn something about the moon. And finally, Crater is an instrument that will measure the radiation environment in lunar orbit to try and get data to help, again, from planning with humans on the surface. Next slide, please.
Spatial resolution for LEND?
LEND does 10-kilometer resolution at the pole, because that's where theoretically at the pole where it sees it all the time. I don't forget the exact numbers, but as you go further away from the pole, you get poorer than 10 kilometers. Next slide. So my other day job is I'm program scientist for LCROSS, which is a co-manifest mission with LRO. And essentially, when LRO went to an Atlas V, the AA realised that they actually had they had a lot of, at that point, spare launch capability. So there was an announcement of opportunity came out saying, hey, you're allowed 80 million. What could you do that would help you collect data to help the vision? And you have to co-manifest with LRO, and you can't affect it at all. You have to be a passive co-manifest. And NASA Ames was the winning proposer, and it came up with a mission called LCROSS, Lunar Crater Observation and Sensing Satellite. And the idea here is that you fire something into the moon into a permanently shadowed region, and you look at the ejector that comes out, and you analyze it, and you look for the evidence of water ice, because the actual ejection process itself doesn't heat the regolith that much. So if there is water ice in the ejector, it will stay as water crystals until it reaches the sun, and whereupon it will dissociate and you can see it. what LCROSS does, which is quite clever, is for $80 million, there's only you can't build that big a thing. But you've got this handy upper stage from the Atlas V called the Centaur, which is big. So what LCROSS is, it's actually it's really a shepherding satellite, small satellite with all the cameras that attaches to the Centaur and LRO. The Centaur fires everything towards the moon. LRO then separates, does its own thing. The LCROSS shepherding satellite fires its small engine to tweak the orbit so that the Centaur, still attached to LCROSS, does probably 2 big phasing loops around the moon, comes back in. You can target to about 3 kilometers inside a permanently shadowed region, and then it then separates the shepherding spacecraft, releases the Centaur augers in, the shepherding spacecraft looks at the ejector, it's about 4 minutes behind at this point, looks at the ejector that comes up, analyzes it with its instruments, sends the data back, and then it augers in itself. So it's quite an interesting mission. The key thing, though, is my only concern, well, I have lots of concerns, but my concern with this is a negative result from LCROSS does not mean that there is no ice. There could be a number of reasons. It could just not hit some. And my concern is that if the LCROSS if it comes back positive, that's great. If the spectra comes back and says that there was water disassociating, then that really helps with water water does exist in the poles, and then you use other instruments like our radar to map out where it is. But if LCROSS comes back negative, I get worry that the press will jump on this as water not found on the moon, and that isn't the case. It's a single data point where a negative doesn't mean no. Okay, next slide. My last couple of slides are the idea behind mini-RF is there is contentious current data that there could be ice, but it's an enigmatic. It's certainly from a physics point of view, it's totally feasible that ice can exist in the permanently shadowed regions. And the goal behind mini-RF is to do as good a job as you can do from orbit in order to try and detect where ice exists. And the way to do that is, first of all, to do it multiple times. So we're in a polar orbit, so we see we'll see roughly the same strip of ground every 28 days. So if we find something that's evidence for ice in a crater, and we see it 12 times with all slightly different viewing geometries, you can start to make the argument that it's volume scattering because of ice, it's not just surface scattering because of rocks. Also, to help make that argument, we use a unique hybrid polarity architecture. Typically, as I mentioned, for looking for ice, you broadcast one circular polarization and you receive both circular polarizations. We do something different. We broadcast nominally right circular polarized, but we receive horizontal and vertical polarized signals and the phase information between them. With those data, we can do a lot more. First of all, we can generate the right and left return signals, but we can do much more than that. We can generate the Stokes parameters, which can be used to reconstruct and investigate the nature of the backscatter field far more than if we were just receiving circular polarized signals. And next slide. So overview, there are 2 mini-RF instruments. The one on Chandrian-1 is single band, it's S-band, it's roughly 12 centimeters. So not only will you get, even separate from the ice question, key data that we will acquire, which is key to this audience, is first of all, we will map out the interior of all the permanently shadowed regions so you can see what they're like. And also, for both lit and dark regions, even though the pixel size is 75 meters per pixel, within that pixel, the brightness level you get is a function of surface roughness at the 12 centimeter scale. So you'll be able to map out which places are more hazardous than others from a landing point of view. So the instrument on Chandrian-1, 75 meters per pixel, we have 16 looks, which means that we see the same point on the surface 16 times essentially as we go by. Think of that as a good signal-to-noise number. It will be high-quality radar data. And we look off at about 33 degrees angle off to the side. Whereas with LRO, it's a more advanced instrument. So first of all, it's 2 bands. It's S-band and X-band. X-band's about 4 centimeters per pixel. So again, we'll be able to compare data with both bands to look for, is it water ice rather than roughness. It has a zoom mode, which is about a factor of 5 better than the baseline, about 15 meters per pixel. Also, we're pointing out at a different angle, and that's intentional. So even if we take the S-band baseline data, which normally is identical to Chandrian-1, the fact that we get these data at 2 different angles and we can analyze, see how those images compare. Again, we'll provide more information on is it ice or is it surface roughness. And also we have an interferometric mode on LRO in that we can take two strips of radar data which have almost exactly the same viewing geometry and combine those data to do fairly high resolution topography, including topography inside the permanent shadow. And as my so the conclusions are the lunar poles are the ideal lunar outpost site, which is, if you're going to take away anything, you can take that and leave. I mean, if you look at the moon as a whole, it's certainly the easiest place to establish permanent, sustainable human presence, which is, after all, the goal. The best areas of illumination are relatively small and dispersed. However, constant solar energy is a possibility, but it will likely require multiple sites in order to generate that power. Ice is a significant resource, and we hope, and many of us think is there, but it isn't a requirement. You don't, stress again, you don't have to have ice there to make the poles a place to go, and even if it's there, it will still likely be a challenge to extract. You're not going to be sending people into 50 Kelvin for a while, and even for rover, that's tricky. And there are still a large number of unknowns that you want the answer to today, but key data will be available soon. Thank you. Well, I should have paid you money. It's too late now. So yeah, I mean, one of the there are two parts to this.
It's a linked,
Yeah,
it's a linked thing.
yeah.
Because we still don't know where L cross is going to go. Or
No, if we assume the way I didn't have with Mini RF and Chandrian-1, then we actually get 4 30-day windows a year where we get to turn on every orbit, both poles. So it's very likely that by the time LRO launches, we should have had one of those. If we've had one of those, then we will have covered both polar regions entirely, except for the fact, I didn't have enough slides to cover this, because you point out to the side, you naturally get a gap immediately below you, which is of course where some of the key regions are that you want to see. But there are two ways, in the time frame involved, there are two ways to mitigate that. The first is, no orbit is purely polar. It goes 90 to about 91 on a 14-day cycle. So when you're at the maximum off-polar inclination, for one of your strips, you're pulling it close to the pole. So you actually will start to fill in a gap close to the pole. The other thing we can do is a roll. We can do a small roll to bring these strips in. At those maximum inclination orbits, a small roll will put a strip, for example, straight over Shackleton. Whether we get the opportunity to do that in the first 30 days, we don't know yet, because that also... There's the ephemeris, there's looking at the ephemeris data to say, are there such orbits in existence? And then rolling the spacecraft's a big deal because all the other instruments want to point down. When we roll, we affect everything. So that requires negotiations on an individual case. But in principle, yes, the Chandrian-1 instrument will help do what I would call macro-scale targeting for L-cross, i.e. which crater. And to some level, microscale targeting, which is where inside that crater, because they want a smooth surface, no rocks, to maximize the ejector. In addition to that, LRO will be in orbit for about 80 days before L-cross hits. And L-cross can, even though they have to pick the hemisphere before launch, the amount of delta V it takes to fine-tune where near whatever pole they choose they hit is minimal. They don't have to fine-tune their 3-kilometer ellipse until post-launch. So there's also a plan being worked for Mini RF on LRO to acquire data to help with targeting for L-cross, and also the other instruments in LRO, what they can contribute.